Anyway, hi. I know this is a tough slot. This is the 14 o'clock just after lunch. You're already 2.5 days in. So I'm going to try to keep it dynamic and energetic as much as I can so you don't fall asleep, but I hope I won't fail. So welcome. We're going to talk about data-oriented design and entity component systems. I guess we can do the quick show of hands just to make sure you're all awake. Who here has heard about data-oriented design? Okay. And who has heard about entity component system? Okay. Who thinks they understand or have an idea of what it actually means? Okay. Okay, good. You're my audience. You heard about the term. You're probably one of those guys, right? Like, so there's a running joke. If you go to GDC, I have like a kind of a drinking game. If you watch a GDC talk, you pick a number when you watch a talk, like between usually 1 and 5. And if your number comes up, you drink. And the number is how many questions until someone says, by the way, regardless of the topic, by the way, regardless of the top, have you thought about using an ECS that would solve all your problems? It doesn't matter what the talk is about. It will happen. It's a very funny game. You can't really get drunk out of it because it's only one shot every talk, but you know, it is a thing. So I had to explore it, right? Like, because, you know, maybe I have problems. We all have problems with our software. And maybe if I use an ECS, it will solve all of it. The weird bit is everybody tells me to do that, but nobody makes a talks about an ECS. Or very rarely people make a talk and tell me how it solved all their problems. Somewhat, but not entirely. So I'll try to explain a bit my adventure with ECS and how we went. If you look at the popularity of the term, it started somewhere around the mid-late 2010s. And I think the big spike you can see here is a reaction to Unity. Announcing the mega city thing and the entity component system that comes with it. If you're not very familiar with game engines, Unity for the longest time was kind of considered like the quirky indie mobile of video game engines, and it started like kind of hurting them in the sense, I don't know, maybe just pride, but they were like, no, I want to play with the big boys. I want to be the Unreal boys. You know, I want to play in the AAA area. And so that's why they put a lot of effort, and they made lots of big announcements back in the day about like how no, we're also the big serious like engine now. We can have like 1 billion things on the map. We can render a lot of stuff. They made like the mega city demo. I think it was at their own conference. I don't think it's a demo you can find on a specific conference, but it's a nice thing. You have like a big, like, you know, like Cyberpunk / Fifth Elements, a big like mega city with one like car flying all around. There's no loading screen anywhere. It's impressive. It's a tech demo. They're all made to look super impressive. And that's where the whole talk comes about. And you know, I have no idea how this works, by the way. Like, this was supposed to be Google Analytics, and allegedly Sweden and then South Korea are the people who search the most for ECS. It's maybe because in Swedish, like ECS is like a government agency that I've never heard about, but I don't know, I live in Sweden now, so go Sweden. I don't know. I don't think we are using ECS more than anybody else, especially I'm surprised that the US did not pop up as much, but I have no idea. But anyway, hi, I'm Matthew. I'm a tech lead at Paradox, and I'm currently leading the development of some secret stuff that I can't talk about, mostly. But I can talk about some tech. So this talk was difficult for me. I spent last spring. Usually spring is where I start thinking, I need a new talk for the new season because my season starts like after summer. I need a new talk. What do I talk about? And I was like, there is this thing about data-oriented design and ECS I keep thinking about, but I had a lot of ideas in my head, and I didn't really know where that, like how to architect, how to make that like a, you know, like a story that you want to tell, because that's the point of every talk, right? You're supposed to tell a story. You're supposed to have like a thread somewhere. And it was really hard for me. I kind of cooked up a bunch of slides, threw them at my meetup and said, please tell me what you think. And they came like, it was great, which didn't help. But I think I'm starting to have an idea now. Well, actually I have 2 because I've given this talk 3 times now. And now that I have given it a couple of times, my ideas have changed. But let's start with the original idea. The original idea is just about performance, right? I talked about profiling. This is me at ACCU, I think, 2 years ago. It's great that there's the number because I can't keep track. So yeah, I talked about profiling 2 years ago. I talked about multithreading last year, and also 2 or 3 years ago, technically it was a recycle. One day I'll talk about allocations, one day. And we're gonna talk about caches in data locality. This is one way of looking at like, how does this work with the kind of talks I usually give. But after I've given this talk a couple of times, I think maybe actually I can start a series on data-oriented designs. And this one is about the principles of like how does that work, and then like basically how do you implement the storage backend for it, or what are some options you can think about for data storage. So it's quite technical. You will see a bunch of C++ code. You will see some benchmarks. It's the code one. But eventually, I think I will have a second one, stay tuned, that will be more about architecture and design patterns. Because I think this is very, very also needed in the industry, but I don't want to get ahead of myself because we're here to talk about the basics today. So today we'll ask the questions. What's an ECS? What does EC and S mean? What is data-oriented design? I assume some of you are already familiar, but we'll still go back to some basics. What does it mean, cache-friendly data structures? We talk about caches more and more, but I think it always good to reiterate a second or third or 10th time, because you need to get that in your head. And we'll talk about decoupling and coupling. I'll get back to this. So first, where are we coming from? And we're coming from hardware, right? I do love the fact that we write a standard for an abstract machine that only exists in the heads of people who like to debate the wording of the standard. But at the end of the day, it runs on a machine. I have a hardware, my clients have a hardware, I work in video games, my players have a hardware, it's usually an Intel or an AMD CPU. Some weirdos on Mac have ARM, but let's not talk about that. And yeah, that's what runs on. And hardware has a bunch of stuff that is not represented in the standard. If you're familiar with the law of leaky abstractions, which is a very old blog post by Joel Polsky, I think like in the mid-2000s, where he mentioned like any abstraction we can make up is by nature leaky, which means that it's an imperfect abstraction and there is stuff that will not be represented through it. And the biggest one is the fact that, C++, as I think some of the talks previously today have said, like C++ is coded against an abstract machine who is itself trying to replicate an 80s machine, which is itself translated into like a very CISC instruction set that is behind the scene interpreted by your CPU on a RISC operator. Like it's abstraction all the way down, and all of them leak and all of them have side effects. And the biggest one is the one I'm gonna mention here. But first, I don't know if you were there for my lightning talk yesterday. I assume most of you were, because that's the best part of ACCU, and you shouldn't be here if you have not been at the lightning talk. This is the bit you should be. My talks are optional, but lightning talks are where you should be. So I talked about speed very briefly, and some insane performance requirements asked for a video game. And I asked the question, do you really know? Do you have a ballpark in your head of like how much one of those bad boys can compute in like a second or a nanosecond? I think those numbers are really hard to put in our head, so I'm gonna try to help a bit. So I don't think I get surprised myself, and I've been in this hobby for like, I don't know, 20 years at this point. I still get surprised about how fast it is. Like arithmetic operation, most arithmetic operation, they're like add, subtract, multiply. It takes, I think some of them takes less than 1 cycle, which kind of blows my head. But yeah, 0 to 1 cycle is the average. Maybe 2 cycles if your CPU is in a bad mood. And we talk about cycles, right? And I'm not 100% how many cycles happen, but if you want a very simple abstraction, take the number of gigahertz you have. That's the number of cycles per second. But that's the concept of hertz, right? So if you have something like a 4 gigahertz or 3.5 gigahertz, which is like the classic right now for like performance scores. If you have 3.6 gigahertz, 3.5 gigahertz, that's 3.5 billion instruction per second, 3.5 billion adds. You can almost wrap an int in a second by just doing plus plus. Your compiler will probably like that, but if you write it in assembly, you can wrap an int in less than a second. I don't know if you can understand the idea of like you do plus plus on it, you can wrap it in a second on one core. You usually have 16 nowadays. You can do some more complex stuff, including the stuff that my CS teacher warned me against in the 2000s, like division, square root. Oh, don't do that, it's slow, it's bad. Yeah, it's bad, it's 10 cycles instead of 1. Like, sure, I can only do like 300 millions per second instead of 3 billions. I mean, there's an order of magnitude, I'm not gonna deny it. But like, yeah, the divisions are not your problems. You may have issue with division because of like the way cores work and the fact that I'm not gonna get too much into details. Divisions have some, again, leaky performance issues. Square roots though, it's the thing you're like, so square root, that sounds very hard. Yeah, you have hardware instruction to compute square roots since like, I don't know, the 1980s. It's a joke. Your CPU laughs at, will laugh at a square root. And now you can do stuff like SIMD. Actually, your CPU is so funny that usually with the instruction reordering, it's able to do 4 integer adds in one cycle. Don't ask me why, but people at Intel are really good at the job. And we've seen that you can explicitly do even more, right? Like it's single instruction, multiple data. You can do like, I don't know, you can ask for like 4 square roots to be done in one instruction, and it will actually do 4 square roots in the time of 1. It's magic. I've barely scratched the surface. But the problem is, and this is why maybe you have never observed the fact that your CPU is so stupidly fast, is that as someone has said, I think it was Guy yesterday when he started talking a bit about the history of computing and storage, memory hasn't really followed. Like your memory bus doesn't much faster than it ran 20 years ago. It runs slightly faster and it's like quad pumpered and some other like very fancy terms. But in terms of magnitude, it hasn't like gone up to par by any means. Like if you think about your 486 or whatever, like early 90s CPU, like the CPU ran mostly at the same frequency as the memory bus, and then we started having like frequency multipliers. Like I think the first one was 2. Like the CPU runs twice as fast as the memory bus. Nowadays it's like 100 times, at least. Like your memory bus runs as a couple. Your memory bus runs in megahertz. Your CPU runs in gigahertz. Maybe not like 1,000, but probably like 10 times at least. So there's this field called physics, right? I suck at it. I'm bad at math. I'm bad at physics. I think it's been explained in the past, but there's this thing called physics, and physics really likes, like, current can only travel so fast and do that kind of things. So if your data is physically collocated on the chip, then you can basically operate at the same speed as the actual chip. If it's on other chip, then it needs to travel the distance. There's some electrical current involved, some buses. I don't understand all of it, but I can understand that it's not as fast. So, like if you read something on a CPU register or in L1 cache, I know this is technically not exactly the same place, but honestly, unless you're chasing the last bit of performance, it's the difference between reading something that is in cache and world cache or register is the same thing. Like you will basically see the same kind of effect. That is fine. Like you will just, you can access all that data. The CPU needs it. If not, it's gonna have to fetch it from memory, right? So if you read a pointer to somewhere, if by luck that value is in cache, then it's fine. If it is not, you have a problem. So here is a diagram to scale for a modern computer, roughly. So this is your CPU on the left, and this is your RAM on the right, and this is like the 6 degrees of separation between the two that are causing so many problems. It's about 100 nanoseconds to go from one to the other. I think it's round trip. Let's say it's round trip. Honestly, like the actual numbers don't entirely matter. I tried to look it up on the internet. This is the best figure I could find. It's 100 nanoseconds, which if you're very good at math, which I'm not, you already realize that that's not really working well with gigahertz. Like there's not enough nanoseconds in a 100 nanoseconds in a second to work well with gigahertz. So that's why, right? It's about 100 cycles if your CPU runs at 1 gigahertz. Let's say for the sake of simplicity, let's remove those numbers. It's just 4, 1, same number. We're doing physics. So yeah, it's about 100 cycles, right? So let's move that up and say, okay, what if instead it's in L2 cache, which is physically on your CPU nowadays? And when you buy an Intel CPU, it tells you how much cache it is. It's because it's on the chip. And because it's on the chip, instead of 100 nanoseconds in the memory bus, it's 4 nanoseconds, which is 25 times faster. Yes, I just redone the math in my head. If it's in N1 cache, it's half a nanosecond. And if it's already in a register, it's 3. That's why I say L1 cache and registers are basically interchangeable at this point, unless you really care about that 0.5 nanoseconds. But I think you have other problems way before you have that 0.5 nanosecond problem. So we can also normalize this because we like normalizing things sometimes when we do some stuff in video games. So that's, yeah, a scale of 1, which is 1 being accessing something that is in hot cache versus something that is in somewhat hot cache, like lukewarm cache, right? That's 8. And then something that is in actual RAM, so not cache, a cold cache, 200. And how many of you have seen Mike Acton's video from like CppCon 2015? Okay, cool. I painfully recreated it in Google Drive, so you will see an amazing animation. Because I think it really gives this. I haven't never found a better way to express to people what that 200 factor means. Okay, so I'm gonna show you something. I'm gonna try to fetch data from L1 and from L2, then from RAM, and we're gonna do the animation to scale. So I'm gonna fetch from L1 cache. Did you see it? I'm gonna make it again. There you go. That was your 1, okay? And we're gonna read from L2 cache. You managed to see it, right? Like it's not like this one is just poof. This one's like, you have time to register. Your brain has time to register. You know, you can apply the brakes. You have time to see it coming. Now let's fetch from RAM, all right? Slowly getting there. That's why I can, halfway there. Yes, yes. You almost got it. You almost got it. Yes, we have it. Cool. You know what your CPU is doing behind while you're waiting? Nothing. It can't do anything. I mean, if you're lucky, it has a bunch of other instructions in the pipeline that happens to not rely on that data, and it has a very smart internal scheduler that will try to execute as much as it can. But most of the time, it will just wait. And I'm not talking like, you know, like IO wait, like you would do on a blocking system call. Because, you know, when on a blocking system call, what you actually do if you start doing like a read or write on a socket or a file, you actually yield the CPU back to the OS, and then the OS will wake up another thread. It will start doing stuff. We're talking hardware level. Your CPU is just blocked. It waits. Nothing else will happen. Another thread will not spawn. It'll just be there. You wait. Technically speaking, it's because 100 nanoseconds is not long enough for actually committing another CPU process on it. That's just not worth it. So you just pay the price. And it's a high price. It's a very high price because, again, we're talking orders of magnitude slower than doing an arithmetic operation. By the time you have increased your, like, if you, let's say you want to fetch a value in memory, increase it by 1 and then put it back, you'll pay 200 cycles to, 100 cycles, let's say. You'll pay 100 cycles to fetch that value. Then you'll pay 1 cycle to increase it. And then, depending on your cache system, you will pay between 0 and 100 cycles to put it back. Because, you know, some cache writes actually have a way to not that to be done in async, and so you don't wait for that to actually happen unless you have further instructions that depend on it, blah, blah, blah. But what I mean is fetching the data is 100 and actually doing something with it is 1. And even if you want to square root that data, it's still 10 times longer to fetch it than to actually compute the square root of it. Like the read is 100%, is 10 times more expensive than the actual square root. It's like if you saw a number and your teacher told you, like, give me the square root, you would spend like 10 minutes just reading the number, and then 1 minute just writing the answer, which is not usually how that works. Like that's the opposite of what we expect, right? Reading is easy. You can read the question, and then you have to think a lot, oh, how do I do that? Because math is complicated. It's the opposite. Luckily, we have thought about this problem because it's not a new problem. It's just being aggravated by the fact that CPUs have gotten faster and RAM haven't. So we have had caches, L1, L2, L3 to some degree. This is why every CPU advertised bigger and bigger and bigger cache every time. And with like 8, 10, 16, 24-way associative. This is to try to alleviate that. And there's a question of data locality. How many of you know how the cache line works? Because I have a couple. Okay, that's not that many. That's maybe half the room. Cool. So that you will like this, hopefully. So luckily, when you're fetching like data on the memory bus, you're not fetching 1 byte or 10, or let's say like 8 bytes. You're reading like a 64-bit integer, right? If I actually ask the CPU like read this bit in memory, the memory bus knows that it has latency, but it can somewhat compensate by having some throughput, right? It can fetch a bit more than just my byte. So what it will do, it will fetch the entire thing. So, you know, like there's a modulo operation, but basically you take that, you do modulo the number of entries, and that tells you like what's the, which thing you find on. And on most like modern CPUs, it's 64 bytes. So assuming that each one of those is a 32-bit integer, this is how many you have, 16. So every time you read like an int, you actually get 16 int back for free. And the cache works the same way. The cache will store 16 bits. We'll store the equivalent of 16 ints when you read any memory address. It will load everything around that. So basically it means that if you keep reading around it, it's free, right? Because it's already there, it's already stored in the same cache line, you don't have to do a second memory fetch. And actually, engineers at Intel are really trying to save you some from yourself. So they realize, if you keep doing this, you know, there's a high chance you're gonna continue So when you start hitting that mark, there's a system called prefetch, in which your CPU will be like, you keep increasing those memory read addresses. And I'm gonna be a brother, and I'm gonna start in the background downloading the next one, because I kind of assume you're gonna need it. And usually it's correct, right? If you're iterating or just jumping through memory around there, like, yeah, I think you're gonna need this one. So by the time you go to the end with some luck, it's already preloaded, or at least you will not have to wait the entire 100 nanoseconds. And you know what? They also understand that sometimes you want to go the other way around because people do backwards. It will also work. Eventually, it will say, hey, you're going downwards on these addresses, like you're on the stack or something. I'm going to start downloading the next block for you. It is basically, you can see, I say download and upload, like it sounds like I'm talking about files, but this is the same idea. It's like, I'm browsing entries in in an image gallery, right? You start displaying images one by one. I'm not gonna load them one by one. I'm gonna load them 10 by 10. And as soon as you start hitting the sixth one, I'm gonna probably load the second page so you don't have to wait at the end of the gallery page. It's the same idea. We are trying to avoid you being stuck on a loading screen because nobody likes loading screen. That's what we were talking about yesterday. Well, I mean, I like some of them. They have cool art, but users usually don't like that. So basically, memory access is slow, but caches can alleviate a lot of that as long as the CPU is able to predict the access pattern. Unfortunately, it's not very smart at predicting access pattern because it can only predict so much as going up and going down. If you do anything else, like, I don't know, just a prime number integer sequence or whatever, any like Fibonacci sequence, whatever other numeric series that is not plus plus or minus minus, you have all bets are off, and you just rely on hope that you will actually have the next bit of data already pre-cached. Else, you're gonna hit the 100 nanosecond barrier every time. And again, that makes the difference between like if you do a loop that you just go over like an array and you try to access data, you will. This is why you get like if I sum an array in a random order, it might end up being 100 times slower than just summing the same array from 0 to n or n to 0. This is why. So yeah, if you want one simple takeaway from that first part, linear access good, random access bad. That's the simple and easy takeaway. Cool. So this is an observation, right? This is not a solution. This is just like, oh, this is the life we have. This is how we have to work. The question is, how do we work around that? And I think data-oriented design is a response to that thing, is a way to try to work around this hardware limitation that, again, comes from hardware. Like nowhere in the C++ standard or any language standard for that matters, you will have a lot of concern about this thing because this is not an actual language concept. It's a physical hardware limitation. But we ship on hardware and we have to think about how the hardware works because at the end of the day, that's the only thing that matters. I'm not running my CPU in an emulator. Maybe one day I will. Will it actually emulate the cache slowdown if we solve it by using some like alien technology? I don't know. But that's not an actual concern. My concern is I'm shipping on a given piece of hardware and it has this problem. I have to work around it. So the idea is like, okay, well, we can't really solve it on the hardware way. We just have to work with it. So how about we try to architect our code and our data structure so our data access patterns helps the cache and helps the fact that it's fetching data blocks in that fashion. So the idea is usually work in bulk. Like the enemy of data-oriented design is usually the one case. You know, when you do one thing, then you do another unrelated thing, then you do another related thing. No, it's do bulk. And I mean, I don't think it's a very novel concept. If you ever work with like databases or anything else, you know that batching is usually better than doing one operation at a time. It's true for just about a lot of things we do in computer science. Just batches are usually more efficient. It's the same idea, but with memory access. Batch memory accesses, so you don't have to pay the cost of downloading the data twice, or n times for that matter. And that usually leads you to writing pure function with no side effects, which makes functional programmers somewhat happy. Actually, technically, it's not entirely true because, as we saw in the previous talk, pure functional programming is entirely immutable. Usually what you do is that you have one input that is an array that is read-only and another one that is mostly write-only. You have an input and an output. You could model that as just the output being the return value. It's kind of semantics at this point. Concretely, okay, let's see some code. Maybe that will wake everybody up. So let's say I have a very simple video game. I have units in the game. They're very basic. They have a 3D position. They have a 3D velocity, and they have HP, because we want them to die eventually, or I don't know, something happens. So it's a float free, so it's free floats. I did not bother explaining what the type def is, but it's basically, you'll see that in just about every video game ever. It's a struct of free floats, right? X, Y, and Z, and your free 3D coordinates. So you have a position, you have a velocity, and you have HP. That's the classic. Like, I don't know, if you intuitively make a video game, that's probably what you think, right? Okay, I'm gonna have a unit, and conceptually, it's a thing that has a position, a velocity, and HP. That's what we're taught in school. That's the most classic way. And to be fair, that's not a bad way of thinking, right? It's very easy to reason about it. It's very explicit in the relationships between the unit and its members. It's a unit. It has a position, a velocity, and an HP. Sadly, it's not that great for cache, and we will spend like the next 50 slides explaining why. But on the right side, you have this maybe weirder idea of thinking, what if instead of having like a unit being those three things and then all the units in the game being a vector of all those units, what if I have a struct that is 3 vectors with all positions, all velocity, and all HPs, with like an assertion that all those 3 vectors have the same size? And that's all my units. How confusing, how weird does that? Have you ever seen something like that? Can I have a couple of hands up? Okay, that's again half the room. Do you ever have like, does that look weird or a bit? Okay, it's fine. So let's talk layouts. We're going to talk about memory. So this is your unit in memory, right? We have no padding because we're using only 32-bit constructs, like floats are 32 bits, ints are 32 bits, assuming we're not on a crazy platform that like makes 16 bits integers or whatever. So that's it. That's our structure, right? It's 12 bytes of position, 12 bytes of velocity, 4 bytes of HP. That's my struct. That's my classic way of doing it in OOP, or even like you say OOP, but in pure C you could write that too, right? You notice I haven't put any public or private or anything. It's a struct. Cool. And that's how an array of this unit would look in memory, right? And I colored basically the fields. So, you know, like if you start having like, let's say for example, for simplicity purposes, like in every sequence of 2 units, this is how it looks like, right? So my first, like, I don't know, X bytes of data in my vector, or like the position of the first unit, then the velocity of the first unit, then the HP of the first unit, etc., etc. That's how my data is laid out, right? That makes sense. We all together? You all with me right now? Good. All right. So now let's look at what we do with it. And let's say I look at my video game. It's a very simple video game. It doesn't do a lot of things. Basically, every entity just keeps moving using its velocity. So I have an update position function that I run every frame. The only thing it does is it takes the previous velocity and it applies it to the position. I'm really bad at math, but I understand that it's just a vector add, and that's it. You just do a plus on each field, field-wise, and you're done. That's how everything moves. Every update, you take X, Y, and Z, and you add dx, dy, dz, and this is your new position. Amazing. Then you have another thing that you apply some damage. So you take the current HP value and then you increase or reduce it. I don't know, maybe there's like, it's a simple simulation. It can just even be a random dice roll, right? Every tech, every frame, my units either gain or lose HP due to a random dice. Fine. And finally, we're gonna render the thing. And basically render, what it does is it takes X, Y, and Z, and then it does some math to say, is this X, Y, Z position visible by the game camera right now? If yes, render it. If not, skip, go to the next one. Okay, and that's the most like basic rendering engine ever, but that for the sake of this talk, that's good enough. So that's the 3 bits. Do you start seeing a problem with that? Maybe. I see some yes, I see some maybe. Let me show you. So I'm gonna put in color the memory bits that we actually read, and I'm gonna leave in gray the one that we still have to fetch, because you know the cache works in bits in bulk. But we don't actually exercise, right? That data is fetched and then immediately thrown away. It's again like you download, like let's say you're downloading totally legally downloading like a series of 10 episodes, and you actually care about the free in the middle because that's the one you missed. And you still downloaded the whole archive, and you're like, ah, fuck, it would have been great if I could only download those 3, right? It's the same idea. So if we start by update position, it still accesses most of the fields. So it's not too bad. You know, like there's this one, like 4 bytes. Every line, there's 4 bytes we throw away, and twice, I guess, because we have 2 units per cache line. Like, I don't know, that's 1 in 7. 1 in 7 entries is wasted. It's 1 to 7 ratio. I mean, you can live with this. I think I would live with this. Okay, now let's do damage. Now you start seeing a problem. I'm fetching a lot of data, and I throw most of it away immediately because I don't care about it, because my operation is trying to take damage. It's not trying to do anything with anything else because the systems are unrelated. So it just goes like, oh, okay, give me the entire structure, then touch that one int. All right, throw all the memory away, fetch this next memory, I'll update this field, and then continue. Not great. And then we go to the renderer, and it does the same thing, right? For every struct, you will read the 3 first integers and then throw the rest away because it doesn't care. And this is slideware, by the way. So I think most games have more than 3 fields on every unit, right? You will probably have, I don't know, I look at a guy who used to work on strategy games. How many fields per unit? Yes. The answer is yes. You know, how much do you want your simulation to have? Like, you know, you can have just attack and defense. Or if you're a crazy guy like me or guy, you can have like, I don't know, how many players like to have in a simulation, like speed, armor piercing, armor, how many guns you have, what's your morale versus your HP. We can be there all night. So, and most of those updates will have the same problem, right? They don't care about all those fields. They care about only certain fields. Now, what if we do it this way instead, right? We have 3 vectors. They all have the same size. That's a prerequisite, or else we have a problem. And one of them is just a bunch of like XYZ. The other one is a bunch of DX, DY, DZ. And the last one is HP, so a bunch of ints. That's our 3 vectors. And now we run update position. It's going to read the memory of the first vector. It's going to read the memory of the second vector. It's never going to touch the third vector. That sounds pretty good. We're not wasting any memory here. We're only fetching the data we need. HP, same thing. We're only reading the last vector. That's the only thing we'll ever put in memory. We'll never bother loading the rest. And then we do rendering, same thing. Our render thread kicks in, and it only reads the first array. We'll never bother reading the second and the third one. We'll never bother importing its cache line with it. And you may ask, especially on the first one, but Matthew, I have to read 2 different vectors. Is not that going to be a problem? And no, because caches have this thing called associativity. I maybe don't want to delve into it too much for hours. But this idea is like, basically, it has a number, like from SSCTV, like 8, 16, 24. Roughly speaking is how many array can you read in parallel and still basically have all of the current, as a zip view, for example. It all have like my current segment in different cache entries so they don't like kick each other out. Like modern crazy CPU you can buy have like 24 associative thing. Like you can have, you could be scanning 24 of those arrays in parallel. And with some reasonable luck, you will have all of them in hot cache at the same time. So the idea is that we make transforms, which are very small loops that operate on an array of fields. We minimize the amount of cache that we actually read or write during the update. We try to minimize waste because, again, fetching is expensive, not computing. This is the main thing. Accessing data is expensive. Doing something with it isn't. I mean, it is, but in comparison, it is not. Once you have solved this, then you will start going back to like, oh, that computation is expensive. But right now, it doesn't matter until you have solved this problem. And I'll go back to that later, but you may have noticed that, for example, like update position and hit and take damage do not use the same field at all. I could update position on one thread and update the HP on another thread. Even if my math for HP is super complicated because I use like the most complex random algorithm that blah, blah, blah. I could run both on 2 different threads because I can prove right now that those 2 are basically not accessing the same structures. And that is by definition thread safe because they don't share data. With the other one, this one, this one, it would be much harder. Because if 2 threads are accessing this guy, I have to look at the actual implementation to figure out, are they accessing the same field? Or could I technically pass this unit, a non-constref unit, to 2 different threads? because I know that implementation-wise they don't use the same. They don't use the same thing. Keep that in your mind. We'll get back to it later. All right, where were we? Somewhere there. Okay, cool. Now Freddy's here, so I have to use Quick Bench. Who here has heard about Quick Bench? Cool. Now you have all heard about Quick Bench. You can ask Fred after it. This is the first time I see Quick Bench at this thing, actually. Good. I'm the first one. Quick Bench is amazing. Every time you have an argument with a coworker about is this thing faster than X, it's basically, you know Godbolt, right? You've heard about Godbolt, Compile Explorer? Most of you. Who has heard about Godbolt or Compile Explorer? Okay, most of you. Cool. So you know you can eat some code in it, and then it shows you the assembly. That's one way to resolve arguments with colleagues. The other one is Quick Bench, which basically allows you to make an online Google Quick Benchmark, like macro benchmark, and you can throw both of your codes in one thing, and then click a button, and you get some nice thing. You can follow this link. I should have put a QR code because I realize it's horrible to try to type like this thing, but you can see it in the slides later. So I benchmarked my thing. What I did, I think, is I created about like a million units with random values. And then I run the three steps one by one, right? So I update all the positions, I do damage, and then I simulate a render pass that just does like some math to just see is this visible or not. It's like a very simple like a visibility check. It's not very subtle, but it just gives the idea of like how much does the data cost. And you will see that it's not that big of a deal, right? Like I just told you to rewrite your entire code base to just change the way you write structs. And you gain what, like 10%? Maybe 20? I should have take a screenshot of the, because actually if you put your mouse on it, it tells you how much faster, but I failed. So yeah, you have to, you can eyeball, right? Eyeball 15% maybe, 10, 15%. I don't know. I'm not sure I can tell you like, who will rewrite their code base or their structures to get 15% like this? Okay, so we have two people here. I respect that. You probably work in finance or something, no? Not even. Okay, cool. That doesn't sound like a lot. But remember what we talked about this being slideware? Like, in reality, let's be honest, your unit struct, as we said before, is not that small, right? It's more like this and a bunch of other fields. I don't have time to put my entire game into Quick Bench to see how much fields are. So we're gonna abstract and simulate that by just having padding at the end. I'm just gonna create a struct. I'm gonna call it padding. And I'm just gonna shove it with bytes. I'm gonna be very nice. I'm still gonna keep everything that we actually care about of the unit at the top. So that's technically not the perfect benchmark, because on a real code base, you might have a lot of gaps between those fields too, with like more stuff that has been added over the years. So that's a very easy way to simulate what happens if we do that on an actual realistic. It's a simulation of the actual thing. So let's see, we have 32 bytes of extra padding. That's not much. That's for ints. Now we start saying, we start getting like, I don't know, I don't do math, but that looks faster to me. Like, I'm not saying twice as fast, but maybe a good 75% faster, something like that. Now we're starting to talk. And again, I've added 4 ints to your structure. Sorry, 8. I've added for like 4 pointers or 8 integers or 8 floats to your structure. And already you start having this problem. Now let's add 64 instead. Oh wow, now it's twice as fast. And now let's add 124, and now it starts to show very fast. Fun fact, that allows you to tell what's the cache size on any given machine if you run a bunch of those benchmark, because you will see that it goes linearly with the size, and then you get a big gap because suddenly one entry doesn't fit in L1 cache. Then you'll see a second gap when it starts not fitting in L2 cache, and then you'll see a third gap when it starts not fitting in L3 cache. It's a very interesting, like, empirical way to figure out your cache size if you really want to do this experiment at home. Cool. So now that maybe I've sold you on the idea of changing the way you write structs, what if we try to formalize this as a design pattern? And maybe, what if we overdid it just a bit? All right, let's talk about ECS. So the idea of ECS, or entity component systems, is we bundle like fields in components. So for example, positions would be a component. All the positions, like my vectors of position would be the position components. My velocity would be a component. My HP would be a component. Okay. So every object in the world has an ID. It doesn't matter what it is. It's an entity ID. We can talk later about what kind of ID you can assume, but it's a unique ID, right? Every time you spawn something in your world, or in your world, in your simulation, in whatever your application is, it has an ID. And then each entity can have an arbitrary number of components. And you can usually add or remove components to existing entities. So then you create systems. And what systems do is that they take a selection of components, like usually a component tuple of one to many components as input or output, and they operate on them. And basically what the system does is say, okay, fetch all the entities that have those components and pass them as some form of a zip view to that function and write to the output set, which is also like a zip view, like just a mutable one. That's it. Gather all the entities and apply the transform in bulk. So if we go back to what we were doing before, how does that work out? So a unit is an entity, for example, right? It's one of the things in my game. Actually, it's the only thing in my game right now because this is a very slideware game. But okay, one type of entity we can have in our game is a unit. And a unit has three components. It has a position, it has a velocity, and it has HP. I did not bother highlighting it, but because it's already just HP. Cool. And all those things are systems. Because update position is taking a zip view of like positions and velocities. Damage is taking a view of HPs, and render is taking a view of positions. We can then, in the theoretical and pure way of ECS and how it's been designed, anything can have anything. So for example, let's say some of my units are controlled by AI. They would have an AI component that like gathers data about how it's supposed to behave. Some of them are player controlled maybe. So they don't have like AI control. Maybe they have a player controller data instead, which reminds me like what was the last key press that the player did? Something like that. And then you can go all the way. You can say, well, maybe the game does not have units only, right? Maybe it has like, I don't know, like objects, like immovable objects, like buildings, for example, because they're like blocks or whatever. But like, let's say it's a 3D game and my units are like spaceships. Let's say maybe we have planets. And planets, they also have a position, but they don't have a velocity or HP because they're just immovable object. I still need to render them. So they still have like a position component and probably like a model or like a 3D model component, some 3D rendering data, but they don't have velocity, they don't have HP because they never move. And technically speaking, my render pass wouldn't care, right? It would just say, this is all the objects in the world that have a position that I probably want to render, go through all of them, render them. And then same way, okay, anything that can take damage in the game, just grab all the things that are damageable and then do damage to them. You can start seeing like some concepts basically appearing, right? The concept of something that can move is a thing that has a position and a velocity. The concept of something that can be drawn is something that has a position. A concept of something that can take damage is something that has an HP component. You can start creating things. They call them archetypes, usually. So the efficiency comes from both breaking the objects into smaller components, because then you can do some funny multi-threading stuff, but also the fact that since they're broken in dense arrays that are only containing the relevant data for the given operation you apply in bulk, it's very memory efficient in terms of fetching versus computing. And now the rest of this talk, or maybe like a part of the rest of this talk, will be how do we implement this? So I'm not going to tell you how to implement an entire SCS in like 45 minutes because I don't have all the time, but I can give you some pointers. And more importantly, I'm not entirely here to tell you how to implement your own ECS, but more like what are the data structures we use? And maybe there's something you can take away for yourself without going back to your boss and say, oh, we need to throw everything and make ECS now because that's the future, because it solves our problems. So here's what we want out of our data structures, because again, this talk is about data structures. The first thing we want, right, and the main thing we want out of it, the reason why we made this whole thing happen is we want the fastest possible iteration through all the instances that have a given component, right? This is where we live. This is what we want. We want, say, give me all the X's that have X and Y components and just iterate through as fast as possible, as if basically those were two vectors with the same index sequence. That's basically the ideal world we want to be in, because as far as I know, on modern CPUs, you can't bet two vectors that are ordered the same way. in a view if you want to iterate to something that has 2 components. Someone has a better idea, please throw it at me, but I think this is the best we can do. So yeah, as fast as going through an array is basically what we want to do. Then we want somewhat fast unordered iteration of tuples. Okay, so if it's 1 component, as fast as going through an array. If it's multiple components, that gets a bit more tricky, but ideally, we would like to be as fast as doing a zip view between 2 or more arrays. That's the ideal. I keep saying zip view. Do you all guys know what I mean by zip view, right? Okay, cool. Raise your hand if you don't, so I can just... Okay, the idea for zip view is that you have n amounts of containers, and every time you say give me element 0, it returns you a tuple of every of elements x on everything. And the idea is like if it's 3 vectors, we're just iterating over 3 vectors, and due to the way cache line works, we can basically have each array in a different cache line, and each time it's super fast to access like element 0 of each thing. That's the idea for zip. And the idea is like maybe we can constrain those tuples at compile time, because it is actually hard to have a very an absolutely fast version of component, because it depends on ordering, and then you start getting into sorting issues. But maybe what we can do, and what most of frameworks do, we'll say maybe I can constrain at compile time to give a hint to the ACS system. What are the actual tuple combination that I will access, right? Because the minute you start having 10 components, the amount of possible combination of tuples you get gets exponential, well, like combinatorial actually, which is insane and unmanageable. But maybe what we can do is give some hints either at compile time or at runtime that this is the actual only pairs or like triplets that will ever matter. So those ones should be optimized to be like scanned together. The other ones, I don't really care if they're sorted differently. We also still want to be able to look up components belonging to a given entity ID. It's usually not as important because this is the one case, right? It's like, oh, I have entity something. I want to see if it has component X, Y, or Z. Usually when you do that, you fall back into the one case. You're not doing a bulk on things you already know what they are. It's basically the equivalent of doing a dynamic cast, right? It's like, are you an X? Or if you are an X, can I get this thing? And we all know by now that it's usually not the best way of doing things, but sometimes we have to do it. The classical canonical example on a computer game would be UI or like debugging tools. Like I have an object, what are you? Because I want to be able to display its properties to the user. So I will do like, okay, give me component X so I can do a breakdown of its stats. Are you movable? Then give me your speed data. Or you like AI? Okay, give me maybe some AI summary of the AI data connected to this object. Things like that. We still want it to be fast, but it's not the end of the world if it's not the fastest, because again, this is a one case, and one case is not what we're trying to optimize. Some games also will want to have a way to iterate component tuples in a deterministic order. What's the difference? The minute you say, if I want to iterate over a collection in a deterministic fashion, meaning like if I have 5 players on 5 different machines, possibly different OSs, and they all try to go through all those objects because they are performing like some game updates, I want them to go through the same order. It is usually required for MP compatibility, basically because if you simulate the world on computer A and computer B, they need to agree on what the world is at the end. There are other simulation models, for example, FPSs don't rely on that as much, but strategy games usually do that a lot. Like basically every game is running the simulation, and if they disagree, you get out of sync, you get a pop-up telling you your game is out of sync, and they hate that. So we don't want that to happen. And there are times where sadly the order matter, and we need to make sure that it's deterministic and reproducible. If anything, just for tests. And finally, the last thing we want of this container is that if I create something, it gets an ID. If I delete something, that ID is still valid. Like, not the thing I deleted, but every other ID is still valid. I'm not saying pointers. I'm fine with invalidating pointers, but IDs should still be okay. So like, I create an entity, it give an ID 2, I delete 3 other entities, my ID 2 is still valid, and I can still look it up, and I can still find my thing behind. I'm okay with invalidating pointers, because for other reasons that maybe are out of scope for this talk, I think keeping pointer long term in your simulation is a problem anyway. Cool. So I looked at a bunch of frameworks. I'm not looked at all of them, especially not in details, but I have a rough understanding of how they work and how they do it. So I looked at Unity, because that's the big one that started this whole talk, right? The megacity thing. We looked at Entity, which is an open source one that is, I thought was the one that is used by Minecraft, but I think I've heard from people is one of the many that Minecraft uses. I don't want to know, but they have several Entity for, ECS framework for their game. It is maintained by an Italian freelancer, as far as I know, which I happen to know through professional connection. It's entirely open source, and he has a huge blog about how he designed it and how to work with all the systems. It was a lot of inspiration, especially for the technical detail of his talk. I have the link at the end. I highly recommend you want to take a look at it if you want to get to know more. It's a mine of information. Unreal decided that they, despite being the big dog on the market, decided that they still wanted to get into the thing. So last year, after I first wrote this talk, they realized they put something on called Mass Framework. I think it's mostly aimed at 3D rendering and not at game simulation, but it's still like, it's a thing and they're using the same ideas behind it. It's not like they reinvented it. And finally, I looked at Flex because for a brief moment, my company used Flex because we had a C programmer in the engine team who just refused to touch anything C++. So he took Flex because it's written in C. I will not talk about it because it's in C and nobody should use C anymore. Done. Especially if I have to look at the implementation. God's sake, no. Okay, so the main thing we think is like, well, vector is the solution to every problem, right? That's what we've been talking for like 45, 50 minutes at this point. Use vectors, it's great, it's fast. But we can't because we have an ID stability constraint. So we can't just use vector indices as IDs because the minute I delete something behind you, I reshuffle everything else. And that's not good. There are structures that try to be vectors, but allow for gaps. I think there's a proposal that is still a proposal. I still don't think it's been approved. It has been? Aha, good. 26, cool. It's called Colony or Hive. Don't ask me why. Just Zerg reference maybe. Anyway, Hive now. Okay, used to be called Colony, now it's called Hive. So basically it's kind of a vector, but it allows for gaps in it, and they have some various ways of doing skip fields in which basically it remembers gaps in the sequence. So when you're iterating, it tries to jump to the next valid entry. And then when you try to insert, it goes to the first empty entry, unused entry and push something back and then updates it. There are several ways of implementing that. You can have like a bit field on the side, or you can have like each element has a pointer to the next available non-free one. There are different solutions around that. Or finally, we could cheat. Or maybe not cheat that much. What if we just swap to tail every time when we actually remove something with our vector, and then we just have an indirection? Because, you know, every problem in computer science can be solved by an overlayer of indirection. And maybe our overlayer of indirection is also a vector. Let's see how we go with that. So, Colony and Hive have some interesting bits, right? Like it's constant time indexing. It's slower than vector to iterate. Because two reasons. One, you have skip fields, so you have like a branch every time to know if you go to where the next element is. And on top of that, you still have unused entries, right? If you have like a big spike in size, for example, like you make an apocalyptic event in your game that creates and then deletes a lot of entities, and they don't happen to all be at the end, iterating for it, you will still be fetching lots and lots of like empty marked for reuse entries in the data table. There's no way around that. So let's not go that way. Let's try something else instead. What if we do an external index? What's the advantage? Well, because that's the thing, right? Lookup is not actually that important. That's what we said before. Like it's important to be able to do a lookup by index, but that's not what we're trying to optimize. What we're trying to optimize is iteration. So the only thing we really care about is having a dense vector with no gaps. And how do you keep a vector with no gaps at the cheapest price? You just swap to tail every time you delete something. You just swap the element with the latest. It's very trivial to implement. And you always have a very packed vector. The only problem is you break the ordering. But again, we don't care about ordering because ordered iteration is also not a main thing we care about. We care about fast iteration. And again, since maybe this is a thing you want to do in bulk, maybe it doesn't really matter in which order you process them, as long as you process all of them the fastest you can. So you will sacrifice lookup, partially performance, and you will sacrifice some ordered iteration, but you will go fast. And you will also lose the ability to go from component to entity unless each component has a like a back pointer to its own entity ID, which is possible, but then again, it means that every component goes back to having extra metadata that you're actually not using most of the time, unless you actually need to go back to the parent. But we can solve that. Let me show you, because I think it's way easier to see with a diagram, right? So we have two vectors. The top one is our active component, so it's just values, right? Like arbitrary value like A, B, C, D, E, F, G, just to tell you those are values, right? And then we have an index lookup table. And the value it stores is the actual physical index of which entity is where. And at the bottom, you have the actual entity ID that you're looking up. Right now, it's easy, right? I just inserted 6 things in order. So, you know, the first one happens to be at physical index 0, and it's A. The second one, the second one is at physical index 1, and it's B, etc., etc. That's easy. But comes the deletion, right? I want to delete something. I want to delete B. Component number 1. I don't want it anymore. It belongs to an entity that is dead. We killed it. Go away. So the first thing you do is that first you mark it as empty in the index table, right? Because obviously the entity isn't available. So if you do a lookup, you will get a -1, which will tell you, okay, there is no entity 1. So you return not found, right? Or whatever your lookup does, return null, depending on your type of lookup. And then I still need to do something about the storage, because right now it contains the garbage that I don't want anymore. I just swap it with the last one. And then I update entity number 6 and say this physical index is 1 now. And you notice I keep this thing dense. So if I actually just want to do a span view of like iterate through the components, I still only return the top array, and that array is always guaranteed to be a dense array. There will never be any gaps. I will always only be fetching all the data I want and nothing else. And then when I do a lookup, I have to say, okay, like index 6 into the first array, get an ID back, and then you that plus the pointer to base to this one to get there. So yes, you pair an extra indirection. You have to two-step array. Technically, it's still O1 because you're just still doing like 2 constant lookups. But yeah, you do two data access instead of 1. Again, depending on what you're doing, you may or may not care. The thing we're trying to optimize is how fast we can iterate through the one at the top while still remaining consistent and being able to do the other one at a higher cost. Now maybe we want to add something. Well, adding is easy, right? We had it here. Then it's a new thing. So we call it 7 because it's a new entity. And we say it's at physical index 6 and we just push it back. Easy money. Now you might notice a problem with that. If I keep deleting stuff, index lookup will keep growing to the end of the world, right? Because I don't do any index reuse and whatnot. So eventually this thing will explode. Or maybe not explode, but if I have to actually iterate to all the, if I want to iterate through the valid things in deterministic order, I'll have to go through the second array and then skip all the entries that are -1 and then actually look up the other one, which is kind of inefficient and also just memory inefficient, especially because I'll have lots of gaps in this thing. There are ways you can solve that. One of the solutions I've seen is people use the page table. So like basically each entry, instead of being one index, it's like a two level, like a page table basically. So you know the first entry in the index lookup is points to an array of the first 1,000 entities, then the second one, then the third one. I don't like it, but I've seen it used somewhere. It mostly works if you do bulk deletes and then you can just throw away empty pages, but it's still not very great. We'll come back to that. But first, I also want to see, wait, but I've lost the ability to, if I have a pointer to a given component, how do I find which entity ID it belongs to? Because again, we're trying to store only what we want on every component and nothing else. One way to say, you know what, we'll sacrifice 32 bits. Like, hell with it. 32 bits is the extra price I pay for this. And then every component just have like the first 32 bits of it is just its entity ID. It's not the end of the world because entity IDs are stable, they never change. It's still extra, it's 32 bits that I waste every cache line when I read it. it means that it's going to be 1 in X every time. For a very small component, it's a problem. As long as my components are a couple fields, it might be acceptable. But if you're a crazy purist and you're like, no, I want to pay 0 because I want 0 cost abstraction for God's sake, then you can just say, okay, well, here's the index sequence at the top, right? It just if we just rematch every A, B, C, D, blah, blah, blah with its actual ID, and then we can just say, okay, well, we can just have another table and just make sure we keep it ordered the same way as the previous one. And the good thing is, it follows the same rule, right? If I delete something, I can just swap to tail, and it's basically going to be the same one I'm going to be swapping. So all those things will always be matched. That's one solution. The other one is just embed the ID in it, and different frameworks do different things. So it's as easy a 2 and 3 array. It's really easy to implement. Like I've basically shown you all the tricks, right? They add, delete, and then the rest is just lookup, and you can basically guess it, right? It's just a 2-step lookup, and that's it, you're done. Like it's not a hard data structure to implement. And yeah, you can do pages. I don't like it. And this was why mostly what we do instead is that we try to do generation ID instead, which I don't know if you're familiar with sorry, if you're familiar with the concept of generation IDs. Okay, so what you do is you split your ID into 2 parts. So your ID is not a physical index anymore, or not just a physical index. It's a physical index and a generation ID. So for example, let's say I have like a 32 bits ID. The 8 lower bits are the generation ID, and the 24 higher bits are the actual physical index. And what it means is I can reuse each entry, in this case 255 times before I start getting into trouble, which is usually good enough. You might want to increase that to a 64 bits like index, for example, and then you usually don't have problems. You can shift, right, like how much A and B takes. And the concept is, okay, if someone asks me to fetch entity like 11.2, you can read it that way, right? This one is entity 11.2. So it's physical index 2 generation ID, physical index 11 generation ID 2. And I say lookup component something for like 11.2. So what I know is that if I go back to my, do I have my table? No, I don't have my table. If I go back to my index table, I say, okay, go to entry number 11. Then check number 1 is this -1. If it's -1, it means that it's actually, there is nothing in that entity ID. And if not, then fetch the actual ID and check what its generation ID is, and is it the same one? And every time you reuse a slot that uses a previous -1, you just increment the generation ID. And that way, you can be sure that you can reuse existing entries in the past. It takes a bit more work to insert new entries because you have to find the next available index. But that way you can cheat and make sure that you can reuse the same index over and over again. Multiple component cases start getting way more complex, and I'm looking at the time. I kind of want to go brace through it a bit. There are several ways of doing it. A bunch of ECS framework that I've looked at, just you pre-declare the component tuples that you want. You know, we mentioned that, for example, like something that can move is something that has a position and a velocity. That's an archetype. You usually try to name them as concepts, basically. It's the same idea as it's kind of the same idea. It's not really concept, but it's the same idea. You name things by saying, okay, it has X and B, it has A and B. It's that kind of object. Again, you can specify that either at compile time or at runtime, and it will try as best as it can to sort the different component tables in a way that avoids like extra lookups or whatever. Ideally, if it turns out none of your archetypes conflict with each other, you can just make sure that all the relevant arrays just are sorted the same way all the time, and then it's just a zip view to iterate through the component table. And if you can't solve that, because as your ECS system grows and you have more and more entities, you usually stop being able to do that. You need to take other techniques. Unity does archetypes on the fly. That's a bit complex. They have like page tables, I think, of every archetype. And so basically what they do is that if you say that this archetype has component A and B, they will store it in a table of A and Bs. And basically, every time you add a new, you add or remove a component from an archetype, from an object, it becomes a different archetype. So you have some mem copies around that happens. The doc says do not abuse the add and remove entities components all the time because it does trigger like mem moves and mem copies in the backend all the time. Oh, which is a thing I have not mentioned with this at all. We always assume that your things are trivially movable, basically, or trivially copyable. Because again, we're talking about arrays all the time. We're talking about moving things in between arrays. It should be able to be done by a mem copy. If I have to run a move constructor, it's gonna be less efficient. So again, yeah, that's what they say. Adding or removing components in entities can lead to a heavy mem copy. And it doesn't scale super well if you start having lots of archetypes that have, you know, like let's say you have 5 components and then you create like 10 archetypes that all have 3 of all of those. It starts getting weird the way it works. The alternative that entity does is just, it kind of assumes that it will be able to find one that is way smaller than the other ones and then rely on the fact that then you're not gonna have to look up that many things. So for example, let's say we want to iterate on all the entities that have component 1 and component 2. This is what we want to do, right? So what we do is we use the smallest component, the one that has the smallest size as our base, and that one we just iterate from beginning to end. And then for all the other ones, we actually do a lookup by looking at their entity ID. So it's not a zip view. You will still get somewhat random access on the other components, but the hope of entity and the creator of entity is that usually you're lucky enough to have a component table that is way smaller than the other one, so it's not that big of a deal. That's his hope. I don't have first-hand experience about how well it scales, because again, there is not any easy solution to make sure that everything keeps a zip view, because it's just a combinatorial explosion of like, how do I maintain so many arrays that are sorted the same ways? Especially when I start getting conflict in which combinations are used. So that would be the idea, right? Like I start for 1, so I just try to figure out where it is. Okay, it doesn't have components, it doesn't have this component, so I can skip, blah, blah, blah. That's the rough idea. There is some options. You could possibly say, okay, if we do this at compile time and we can prove that only all those combinations are used, maybe you can preset a bunch of like you can make sure that all the add and remove operation will always happen at that level, and then you sort out the problem. But I don't think it's a solved problem. But I know this is getting very technical, so I'm gonna try to wake you up a bit and talk about, okay, in practice, did it solve our problems or not? So this is the bit that gets a bit weird, especially now, because production games at Paradox, the ones I have first-hand experience on, do not use ECS at all. It's a thing people keep telling everybody else to use, but nobody seems to actually have a lot of first-hand experience using. I see guys like, yeah, I heard all the talks. I've never seen anybody use it. Like I said, Mojang apparently used like several of them. Again, sources I heard, I can't confirm. This is just what I heard. I know Blizzard made a talk about how they used it for Overwatch. But that's the only things I could find. Like I find a lot of talks about you should use ECS. I found a very little talk about I used ECS and this is how it works for us. So nothing in development like the secret stuff was not either using ECS when I first wrote this talk 9 months ago. But now we kind of do, but kind of don't. It's complicated. I would like to get into details, but basically I have another talk now. I have another talk. It's not written yet. If you happen to be in Dublin on Monday, I'm gonna run a very, very harsh version by their local game dev meetup. It's undercooked as hell, but it's the second one about design patterns and everything, because this is a whole can of worm when you start doing that. And we're gonna have some questions to answer eventually. So, in the few things I've noticed. First of all, if you have small components and disjoint archetypes, it's easy, right? You don't have to solve, because the main issue, the main technical issue with storage, because we're talking mostly about storage here, is how do we manage to keep accessing all those component pairs or tuples in the most efficient manner. It's next to impossible unless you have a very heavy recomputation that keeps moving things around, or you can guarantee that all those archetypes are disjoint, and then I can just make sure that all those things are ordered the same way. If not, you're gonna have to pay some cost of random access. Probably still better than OOP, but I don't know about which factor. Depends how big your collections are. The other thing that I've noticed in ECS is that they really love to say that every entity has the same ID sequence, regardless if they will ever have shared components or not. And I think that's absolutely insane. I know you have options, but the default on most ECS frameworks is you have a world for your game, and any object you have in your game, doesn't really matter what it is, goes in there, and they share the same index sequence, which is a waste of everybody's time in key space, because I have a bunch of things that I can prove that will never share any components. You may say, well, yeah, but it's software and it might change. True. But also there are some I can tell you from the get-go, they will never share a component. And if they start, maybe we start doing something wrong. And so most of the time you can fix that. Like frameworks will allow you to have several key spaces, basically. And that also makes sure that your component tables stay smaller, because you don't have to keep iterating over components that will never have the second one you're looking for, and then just basically waste your lookup times. And a lot of the time I figure out that archetypes can be defined at compile time. I haven't found a lot of use cases where I make up new like game archetypes at runtime. I think the reason would be that if I start having like script, like if I start having saying, oh, you can write your own systems in script, and I can't tell at compile time which of the data fields you will actually use for that processing. I haven't gone there because I think our script language is slow as hell, and I would rather have nothing to do with it. Maybe in the future, but that's also start getting into having JIT, and I don't want to get there. So let's try to keep it simple. Designers will hate you because designers, especially in all games, they love where everything interacts with everything else. You know, okay, I'm doing unit combat. I'm gonna fetch data from the actual like unit. Okay, cool, fine. I'm gonna fetch data from the type of unit it is, which you can customize because maybe you have your own take on what a tank battalion is supposed to be. I'm gonna fetch data from the guy, the general who is leading that unit. I'm gonna fetch data from the province it's standing on. I'm gonna fetch data from the country it belongs to. Wait a minute, I also have temporary bonuses because you've done a mission. And every time you say, well, the current transform cannot because I have to change the type of archetype they're accessing now, they hate that answer. They don't like that answer. Say, oh, and you end up changing your transform and add more and more things, and your archetype keep growing because you need more and more fields in your transforms. There is a limit to it. I don't want to talk too much about architecture here, but the very raw feedback I started getting from colleagues who have been like a bit more advanced into this on another secret project is they started over-componentizing at first, and then they say, you know what? No, like I want to keep something small, but there is a limit to how small I want it. And then until I have a profiler who shows me at gunpoint that this is a bottleneck, I will not bother splitting it. A unit is maybe we can have like combat stats and like graphic stats, for example, and then maybe location has 3 components, but maybe not make like ECS frameworks documentation will say position and component should be components. Like position and velocity should be components. You should have tables that are 3 ints or 3 floats. I think that's insane. I don't think you should go there. Write your updates as free function first, and then constrain the input by type, right? So you start saying, okay, I want to do an update on my game. I want to do a bulk process in my application. So write a free function that takes a span of A, B, and C's, and then say, well, okay, since I'm taking spans of A, B, and C's, maybe this A, B, and C's could be stored in like an ECS style storage because that's way more efficient for iteration than, I don't know, like a map or whatever storage type you use. So yeah, it kind of sounds like, oh, I used ECS and it didn't solve any of my problems. You know, that's a really bad talk title, and maybe I would not have been accepted if I had submitted this. Maybe I would actually. You know what? Maybe I would. I don't know. But still, like data-oriented approach still is there, and it's there to stay until somebody figures out the magic memory controller that makes all of this completely obsolete. But I haven't heard any research that is going that way, where CPUs will keep getting faster, and they'll keep being just spinning and waiting for RAM access to come and fetch them the data they need to get going. Making multiple components ECS like iteration is tricky. Like I think I gave you the ideas I was trying to go through. There are several approaches. They all could take their own talk, and they all have trade-offs. But honestly, I really like the single data one because it's really simple. It's 2 vectors to implement, and then that gives you a data structure that has like first like a stable that gives you a stable index plus a guaranteed iteration that is just the fastest you can get because it's a dense array. And I think just that, I've used it like already. I'm like, you know what? In some places for a very like bespoke system, I'm gonna have my own index sequence and I'm gonna have my own thing. And then when I do a for each on every entity, it's really just all I want and nothing else. So consider, I think the guy who made it, I did not steal it. I did not invent it, by the way. I think the most implementation I saw come from NTT. I'm not 100% sure he invented it too. I reached him out by email. He said, yes, but I need to write a 5-page dissertation to answer you. And then he never replied again. So I'll see if I get better answers. But he calls it the dense sparse array. Because again, it has a lot of good property, right? It's very fast. It's the fastest in all the iteration I can find. It's constant insert and delete. It's technically faster than vector to delete if you even if you delete in the middle. It's constant lookup by ID. It has ID stability. It doesn't have pointer stability, but arguably vector doesn't either. The minute you push back and you reallocate, you died. And you know, it's not amazing when you start to do deterministic iteration because you have to do an indirection table that might make you bump all around. But it's still better than the list, I guess. And yeah, I did not insist, but your types have to be trivial, or at least trivially relocatable, because it does involve some mem copy and some mem move, and you want that to be as cheap as possible, especially when you have to reallocate the vector to grow, because it is way faster. But since I have a couple of minutes, I would like to go back to the idea of code coupling, right? And maybe this is the interesting takeaway that I should have insisted earlier. So here's the thing, right? We do get told from very early age, programmer age by what I mean, which is usually not 5, but a bit later, that code coupling is bad because you should not be mixing concerns, it hinders maintainability, and we've been cautioned forever against it. And yet, we make structs with lots of fields that technically make sense as the idea of an object, but do not make sense about how we actually access them, because most of the time we don't access all of them, we access a very small subset of them. And it's kind of an all or nothing. And I do a lot of multithreading. I have a talk about multithreading. You may have seen it last year. And we talk a lot about how do I know that I can run 2 transforms at the same time because I have 16 threads. You know how I can tell? I can tell because the archetypes you're accessing are different. And I can't do that if everything is a unit. Well, I can, and I've done it. I've done it by reading the code line by line, going into the function called to prove that they technically will never access the same fields, so it's fine if I iterate on both unit arrays at the same time on 2 threads, because technically speaking, they're accessing different fields, and promise to God they will never change that, and nobody will ever change an innocuous function somewhere and break that assumption. It will happen. And that is why the big gain you get actually is that, you know, the base idea to reason about code is that if you have 2 functions that takes the same type of object or the same span, non-count spans, then I know they're not thread compatible because they're accessing the same collections. But if I split them, then it's fine. And so I guess a very short takeaways, if you decouple your data, you will find a lot of multi-threading opportunities. And this is both an intro and a segue to the next talk that I haven't written yet, because this is kind of how we got to ECS at Paradox. We didn't start with data storage. We started with like, I want a multi-thread stuff better, but I cannot prove that those 2 data structures are not used at the same time. What if I split them? The data storage we use is garbage. It's the same, well, it's not garbage, but it's not great. It's not the best data structure in the world. It doesn't have the blazing iteration speed of all of this, but it's okay enough. And then we say, well, then I can define my transforms as what do they read and what do they write. And then building a scheduler is trivial. And that's the way we've been going, but that's the topic for another talk. Because this talk, was about an introduction to ECS and data-oriented design. So still, decouple your data. There's a lot of things to gain with it. Obviously, cache accesses, cache data accesses, and all that stuff is great. But you will also find a lot of interesting stuff when it starts getting into multithreading. Again, good for cache performance, good for multithreading. Everybody's happy. Both are very related to performance. And yeah, ECS is probably overkill. There's a reason why there's so many talks about why you should use it and so little talks about, oh, I used it. I think it's kind of one of those things we tried and we went a bit too far, too hard. And I hope that from there we will come back and say, there's a bunch of things we can use. For example, that data structure. It's really simple. It takes you like an afternoon to implement. You have enough in this slide to figure out how to do it yourself. I could probably find a reference implementation somewhere and add it to the slides, but it is not hard to do. And from there, you can say, if I start thinking about archetypes, I can start thinking about transforms. And if that's how I reason about my updates, then I can easily build a scheduler on top of that. And furthermore, I think your build should be destroyed. Thanks.